So our final talk this afternoon will be given by Peter Ozsváth from Columbia University and University of California, Berkeley on Heegaard diagrams and holomorphic disks. Peter?
Thank you. Well, I'll try to be as brief as possible. I'm aware that I'm competing against food. I got some words of encouragement from my longtime collaborator and co-author who said, don't be nervous, just say as little as possible. So I have license to say as little as possible. I would first of all like to thank the organizers for the honor of being in such distinguished company. And moreover, I'd also like to, well, we should all thank them for organizing such a lovely event. It's been wonderful. So. Okay, so I'm going to speak about Heegaard diagrams and holomorphic disks, and the material I'll discuss here is largely my joint work with Zoltán Szabó. So our motivation was to understand gauge theory from a topological point of view, and I'll come back to what this means. But the basic point is that what we wanted to construct, this sort of structure, was a way of associating a graded abelian group to a three-manifold, which is natural under cobordisms between three manifolds. So if you have four manifold with, say, two boundary components, then that should induce a homomorphism between the two groups associated to their boundary components. Now, well, there's the question of why on earth you'd want to do this. So I'm going to be a little backwards in my motivation. The basic point is that this is the sort of structure that one gets to construct interesting invariants for smooth four manifolds. And I'll come back to this later. But the other point is that there's a slew of sort of three-dimensional problems which are really four-dimensional problems in disguise, and or at least three-dimensional problems which can be phrased in terms of four-dimensional problems. And sort of having this kind of structure fits very neatly to solving such problems. So let me just state two of them. These were both problems that we were thinking about last year. So one of them is a sort of classical question in knot theory, which is called the unknotting number of a knot. So the picture is that you have a knot, which you think of as a closed string in three-dimensional space. It's knotted and complicated, and you want to make it simple. So you sort of yank. Well, this is sort of something that's difficult to do. You cut it somewhere, and then you reglue it. You sort of pull it up and reglue it. So and the question is that you have some complicated knot. What is the minimum number of such steps required to transforming your knot from being some complicated knot to what's called the unknot, the simple closed loop? And, well, so in the illustration I've given over here, this is called the trefoil knot. I suppose one should verify that this is actually not the unknot, so that it is actually knotted. But once you know that if you just change it right here, then all of a sudden, well, it becomes unknotted because I can pull this down and untwist and get the unknot. Here's another picture. This is the knot which is affectionately known to all of its friends by 810. This knot up here, 810. So the question one can ask is, what is the unknotting number of 810? And you should. Here's something to do, and before we all get our refreshments, you can draw a picture of it and see if you can modify it. In fact, this is a knot which cannot be unknotted this is a knot which can be unknotted in two moves. If you do two changes, then you can unknot it. And the question is whether you could do better, whether one could find a better unknotting. Now, of course, incidentally, you might think this is a silly finite problem. I mean, look, there are 8 crossings. You just go through, change all of them one by one, and see if what your knot is unknotted. That's not the actual problem. The problem is for an arbitrary picture. We've got 810. We think of it as suspended in space. When we just pass one strand through the other, can we suddenly unknot that new knot? And so you can unknot it in 2 moves. The statement is that you cannot unknot it in one. So the unknotting number of this knot is 2. So to know that, you have to exhibit a two-step unknotting, and you need some kind of certificate that you cannot do it in fewer steps. And, well, that's one of the applications of these kinds of invariants. That actually, the point is that this problem can be rephrased as a four-dimensional problem. Let me give a different application, which is the problem of Dane's surgeries. So Dane's surgery is a machine for constructing three-dimensional manifolds out of knots. More specifically, given a knot, let's say in standard three-dimensional space, and a rational number, we can form a new closed three-dimensional manifold as follows. We drill out a little neighborhood of that knot in three-dimensional space. The part that we've drilled out is a solid torus. It's intrinsically homeomorphic to a circle across a disk. And now we glue back in a circle across a disk, but possibly differently. And in fact, the ways of gluing in a circle across a disk are parameterized by rational numbers. The point is that here on the boundary of our knot, there's a canonical so-called meridian, which is a circle which bounds inside a tubular neighborhood of the disk. And there's also what's called the longitude, which is a knot that lives on this boundary, but which bounds a surface in the complement of the knot. And the way to glue in a new solid torus is now specified by a pair of integers, which are relatively prime, p and q, under the requirement that the new meridian that you get is p times the old meridian plus q times the longitude. So from a knot and a rational number, one obtains a new three-dimensional manifold. And one can ask the question, to what degree does the three-dimensional manifold remember its presentation? Does it remember the rational number? Does it remember the knot? And so here are some examples that are meant to illustrate that, well, not necessarily. Here's the simplest non-trivial knot, the trefoil knot. If you do +5 surgery on it, then you'd get the same manifold that you get by doing -5 surgery on the unknot. And, well, if you do 18 surgery on the -2, 3, 7 pretzel knot, then you get the same space you get by 18/7 surgery on the unknot. So this may lead one to think, well, there's sort of no reasonable question to ask. But in fact, there are some reasonable questions to ask in this context. And one such question is, well, all right, so let's try to fix the surgery coefficient and see what happens. And so let me state now a theorem which four of us proved. Peter Kronheimer, Tom Rufke, me, and Zoltan. We proved this last year when Rufke and I were both visiting the Institute, and Zoltan was on the other side of the tracks. So the theorem was that if you do R surgery on an arbitrary knot, and you get a three-manifold which is orientation-preserving homeomorphic to R surgery on the unknot, then in fact the knot has to be the unknot. So this this isomorphism here means orientation-preserving homeomorphism, and but there are cases where one can not resort to that, which is, for example, as a corollary, one can prove that if we do R surgery on a non-trivial knot in the three space, in the S3, then one can never get our real projective three space, RP3, which incidentally is the space you get by doing +2 surgery on the unknot. So I should remark that the case where R equals 0, this was already known by a theorem of Gabai. When R is P over Q and Q is not equal to plus or minus 1, it follows from a theorem of Color, Gordon, Lukey, and Shalin. And for P equals plus or minus 1, this is a theorem of Gordon and Lukey. So in fact, the cases that had not been known were the cases where R is integral and bigger than 1. But incidentally, the case of integral R is actually the case which is the most direct interpretation from a four-dimensional point of view. So these are some some applications of this theory. I've been vague a little bit about what the theory actually is, so I should probably put up one slide at least about gauge theory. So the technique for coming up with this kind of invariant really has its origin in the work of Donaldson, which was mentioned earlier, from the 1980s. Donaldson constructed an invariant of smooth four-dimensional manifolds by looking at a four-manifold and equipping it with a Riemannian metric. Then the physicists kindly provided us with a partial differential equation, which is the so-called anti-self-dual Yang-Mills equation. And Donaldson then looked at the topology of this moduli space of solutions to this equation. And by doing appropriate algebraic topology of that moduli space, extracted a smooth invariant of four manifolds. And in fact, that was an invariant that gave a smooth invariant of four manifolds, but in fact that fits nicely into the picture of a topological quantum field theory that, at least for certain types of three manifolds, was noticed by Fleur also in the 80s, that one could associate to an invariant of three manifolds, which had the properties that I stated in my first slide, by doing a sort of infinite dimensional Morse theory on a functional whose gradient flow lines correspond to the solutions of this four-dimensional PDE on three-manifold across R. Now, this was a theory that was very actively being worked on, but in '94 there was a revolution in this field by the introduction of a simpler class of partial differential equations, the so-called Seiberg-Witten equations, which, again, the physicists kindly provided for us. And in fact, going through the same kind of constructions, one could construct a smooth four-manifold invariant by taking taking a smooth four-manifold, equipping it with a Riemannian metric, looking at the moduli space of these new PDEs, and doing algebraic topology on that. And it was very clear from the very beginning that this is a theory that should fit into the same kind of picture which Fleur had cast Donaldson's theory in as well, that there should be a three-manifold invariant. And Kronheimer and Rufka have been working on kind of the ultimate book, constructing this. But the problem with ultimate books is that sometimes it's not clear exactly when they appear. But there's an ultimate book soon to appear by Kronheimer and Rufka in which they construct this theory. Now, the question that motivated me and Zoltan was this question of whether there is a more geometrical or topological way of constructing these same kind of invariants. And well, there's a different construction which constructs an invariant which we conjecture is isomorphic to the Seiberg-Witten Fleur homology, but in certain ways it's easier to understand. Let me just say very quickly what the framework is. So what does one mean by a geometric construction? So, and to say this properly, let me just say briefly some words about Lagrangian Fleur homology. So I was discussing work of Fleur in three-manifold topology. In fact, he was originally studying problems in Hamiltonian dynamics, and he was interested in a different class of problems where one starts with a symplectic manifold and looks at Lagrangians in that. A symplectic manifold is an even-dimensional manifold equipped with a closed, nowhere, degenerate two-form. A Lagrangian submanifold is a maximal dimensional subspace on which a submanifold on which that two-form is identically zero. And Fleur was constructing obstructions to separating pairs of Lagrangians. And in fact, he constructed a theory which is a graded abelian group associated with that pair of Lagrangians, whose Euler characteristic is the algebraic intersection number of the two Lagrangians. So, and the construction goes by writing down a chain complex whose generators are the intersection points between those two Lagrangians, and whose differential operator counts holomorphic disks. So, so one has a symplectic manifold, one has this pair of Lagrangian submanifolds, and what plays the role in Morse theory of gradient flow lines are holomorphic disks whose left arc is mapped into one of the Lagrangians, right arc is mapped into the other Lagrangian, top point to x, bottom point to y. So that plays the role of a gradient flow line. So this was now, you think, a setup which is quite different from the setup of low-dimensional topology that I was talking about in the beginning. But in fact, there was supposed to be a relationship between these two types of invariance, which was espoused by Atiyah, this Atiyah-Fleur picture, that these gauge theory invariants of three manifolds should in fact arise by having some sort of functor which associates to a Riemann surface, a symplectic manifold, to a three manifold whose boundary is that Riemann surface, a Lagrangian submanifold, and to a closed three manifold obtained as a union of those two things, one counts holomorphic disks inside of this associated Lagrangian submanifold. And, well, so the only problem is that it's hard to come by smooth symplectic manifolds that are associated to a Riemann surface in a natural manner. But, well, let me describe a construction. This is Heegaard-Fleur homology. So one starts with a Heegaard diagram for a three manifold. So maybe I should say that every handle body is the simplest three manifold with boundary that you draw whenever you draw a Riemann surface. Sort of, I think of that as the interior here. And this three manifold with boundary is specified by specifying a G-tuple of circles which are homologically linearly independent and disjoint. So if you give a pair of such G-tuples of circles, then you've specified a closed three manifold. And in fact, the closed three manifold I've specified in this picture is the three manifold S1 cross S2. And just because I'm tired of always drawing pictures of silly three manifolds, here's a more exciting one. Here's a Heegaard diagram for the Poincare homology sphere. So here you're supposed to think of this as a genus 4 surface, where A is identified with A, B with B, C with C, and D with D. So there's a diagram. And now, given a Heegaard diagram for our three manifold, we look at the symplectic manifold, which is called the G-fold symmetric product of sigma. So this is the set of unordered G-tuples of points on sigma, where G here coincides with the genus of the surface. So in this case, we're looking at unordered triples of points on the surface. And inside of that surface, there are, inside that symplectic manifold, there are a pair of half-dimensional submanifolds, which are tori associated to the two G-tuples of circles which bound. There's the alpha circle, which is those triples of points where one point lies on each of the alpha circles. And there's a beta torus, which consists of those points where one lies on each of the beta circles. So these are a pair of G-dimensional tori in this 2G-dimensional manifold. And now one looks at a chain complex generated by intersection points between those two tori and whose differential counts holomorphic disks. And the first theorem is that, okay, there's a little extra piece of information which is less important than cookies. So, you know, if you're interested, then I'd be happy to discuss them over cookies. But the point is that one performs a construction of a Lagrangian Fleur homology in this context. Well, so how does one prove a theorem of the type that I stated in the beginning? One, first of all, needs some sort of non-triviality theorem, a non-vanishing theorem that says that this invariant doesn't vanish for non-trivial knots. And one also needs some kind of theorem which says how this invariant transforms, how it's related, how the invariant transforms when you do different surgeries. And, well, for the second point, let me introduce a calculational aspect for this Floer homology, which we call not Floer homology, which we developed in collaboration with Zoltan, but was also independently discovered by Jacob Rasmussen in his thesis. So the basic point here is that a knot in a three-manifold induces a filtration of the chain complex of that three-manifold, and it's really the filtered chain homotopy type of that complex, which is an invariant. And from that filtered chain homotopy type, one extracts a sequence of chain complexes indexed by integers and a pair of chain maps, V and H, which map to another chain complex, which is in fact just the chain complex for the original three-manifold. That's a piece of this structure. Let me speak about it a little bit from a little bit more distance. So the not Floer homology, here's a way of thinking about this filtration. So a filtered chain homotopy type of a chain complex is a somewhat complicated object to think about, and it's somewhat easier to think about the homology of the associated graded object associated with that filtration. And so I'm going to discuss that object, which is actually a little bit of loss of information from this object that I've talked about. And this is a bigraded abelian group associated to a knot, let's say, in the three-sphere, and a pair of integers, we get then a group, a finitely generated abelian group. And this is an abelian group whose Euler characteristic in a suitable sense is the Alexander polynomial of the knot. So recall, the Alexander polynomial of a knot is the invariant specified by the requirement that the invariant associated to the unknot is 1, and this invariant is a polynomial in T, and it transforms when you perform operations on the knot. If I have the knot with one crossing and I change that crossing, the difference between the two Alexander polynomials is related to the Alexander polynomial of the resolution by this formula. This is the specification of the Alexander polynomial, and the statement is that this bigraded abelian group, if you take the Euler characteristic in one direction and multiply the other direction by this formal variable t, then one gets the Alexander polynomial. So one might wonder whether, in fact, this invariant contains more information than the Alexander polynomial, and the answer is that yes, it does. For example, one of my second favorite knot after the trefoil is the Kinoshita Terasaka knot, which is this knot right here. This is a knot whose Alexander polynomial is trivial, and yet the Floer homology is not trivial. If you set this variable s to 2, then you get z plus z, supported in different degrees. So the Euler characteristic of this group is 0 because these two z's live in different parity. But the nice property of this invariant is that so we compare it against the Alexander polynomial. One statement, a classical statement, is that the degree of the Alexander polynomial gives a lower bound on what's called the Seifert genus of a knot, which is kind of a perfect invariant of knots. It's an invariant which vanishes if and only if the knot is trivial. But we get a lower bound which is not typically sharp, as we see in the example of the Kinoshita Terasaka knot. However, not Floer homology does give sharp bounds. So you're supposed to imagine this as being a group, a finitely generated group indexed by points in the plane. And the statement is that you look kind of at these vertical slices. The last vertical slice where the group is non-trivial is precisely equal to the Seifert genus of the knot. In other words, this is a finitely generated abelian group which is able to detect the unknot. So this is a theorem that we proved last year, but it simply uses just about every piece of mathematics that I know and some that I don't. And it starts from a construction of Gabai, who constructs an object called a taut foliation. From that, one constructs a symplectic manifold. From that, a closed symplectic manifold. And then, using Donaldson's theorems of Lefschetz pencils, one constructs a combinatorial decomposition of the symplectic manifold. And finally, from properties of Floer homology, one obtains this non-vanishing theorem. So this is the non-vanishing theorem, which we use to conclude that the knot had to be the unknot. Now, I would love to tell you about the calculational aspects, but you would probably love to have some tea and cookies. So I think I will sacrifice that last 10 minutes and
Thank you, Peter, for a beautiful talk, and I think we do have time for some questions since the reception opens at 5 o'clock. So,
okay, good.
Michael.
I'm embarrassed to say this story was attributed to me before, which somehow got into the literature. Nothing to do with me. It's really all Floer's idea. I was simply giving an expository idea of what I thought he was doing. Somehow, people turned it around and thought I was making my own conjecture. I think his work. Credit is all due to him.
I see.
One of these misattributions of history that if you don't stop them somewhere, go on.
Maybe you want to say what the symbol in that previous overhead above the U was.
Oh, yeah, why not? That's certainly something I could do. If I could find the previous overhead, which is the non-trivial question. Yes, I can. So in the setup, we have a symplectic manifold, which is the g-fold symmetric product of the curve. And inside of that manifold, there's a complex codimension 1 submanifold, which is those g-tuples where one of the, oh, I'm sorry, I should say this. We're going to work not only in the category of Heegaard diagrams, but in pointed Heegaard diagrams. So that's to say, we're going to pick a reference point z, which lies away from the attaching circles alphas and the betas. And that additional point gives a complex codimension 1 subvariety in the g-fold symmetric product, which consists of those g-tuples, one of which is z. And since we've required that that point be away from the alphas and the betas, we get a complex codimension 1 subvariety, which is disjoint from these two half-dimensional spaces. And therefore, there's a well-defined intersection number between any disk of the type I described in the beginning and this complex codimension 1 subvariety. So we now sum over all the differential of some intersection point x is a sum over all other intersection points y of an internal sum. So naively, one is tempted to say, if we just picked the Lagrangian Floer complex that I stated before, one would just, so by the way, phi here means the space of homotopy classes of disks that connect x to y. So in the classical Lagrangian setup, one would just simply have the coefficient of y to be the sum of all the holomorphic disks. But here we want to separate them. And the way we separate them is to think of our chain complex as really a chain complex over a formal variable u. And now our coefficient is going to be u to nz phi, where nz phi is the intersection number between our disk and this complex codimension 1 subvariety. So somehow this formal variable is in fact what makes the theory non-trivial. If you set it equal to 1, then this theory seems to recapture the first cohomology of the 3 manifold with the z coefficients, and or the second cohomology of the 3 manifold with z coefficients. And it's precisely this formal variable that makes things interesting. So specifying to u equals 1, one gets this trivial theory. Specifying to u equals 0, one actually gets an interesting theory. But when one leaves u as a formal variable, that's when one gets the theory with the most structure.
Yes.
Oh, right. So this is, of course, a point that in the ideal talk I would have made. In fact, you should notice that, and you did, that this theory that I put up formally was a bigraded theory whose graded Euler characteristic is the Alexander polynomial. In fact, there's another theory with very similar properties, which is the Kovanov homology, which is a bigraded theory whose Euler characteristic is the Jones polynomial. And gosh, here are two theories that are extremely similar. The difference is that this one, in its definition, is uses holomorphic objects, whereas Khovanov's definition uses pure combinatorics. And to turn the question around, wouldn't it be wonderful if there could be a completely combinatorial way of constructing a theory of this type? Not on the cipher genus. Not on the cipher genus. There are bounds. There's a work of Rasmussen which gives bounds on the four-ball genus, but presently there's no kind of non-triviality theorem. There's no theorem that if Khovanov's homology is non-trivial, then the knot has to be the unknot.
Final question, yeah.
Two different physical theories, one of which is cipher, another which is about this. Physicists might be able to see how they're related. It might not help prove, but it might be nice encouragement.
So I'd like to thank Peter and in fact all of our speakers for a marvelous set of talks, and as you've heard, you're all invited to a reception over in the Fuld Hall Common Room. Thank you.